Hello, Mr. Betts here. I want to take a look at a couple examples where we are writing the Maclaurin polynomial for a function, and that function is represented as what could be interpreted as the sum of a geometric series. So if you remember, the sum of a geometric series is the first term over 1 minus the common ratio. So if we have a function that's in a form that is like that, then we can take that function and say, okay, this is equal to that if we make the first term equal to 3x and we make the common ratio equal to 3x squared. So the Maclaurin polynomial, I'll call it m of x, is going to be the first term, 3x, and then the second term is going to be the first term times the common ratio. So it's going to be 9x cubed. And then we just continue multiplying by the common ratio. So 27 x to the fifth. Now I'm looking for four non-zero terms. So I have three, I need one more. So 81x to the seventh. So that is it's the seventh degree Maclaurin polynomial, but it's the first four non-zero terms of the Maclaurin polynomial for 3x over 1 minus 3x squared. I also want to determine the radius of convergence, and I'm actually going to change this question to the interval of convergence. Remember that a geometric series converges when the common ratio is between -1 and +1. So in this particular case, the common ratio is 3x squared. I do want to point out that 3x squared is always greater than -1 because if x is 0, it's 0, which is greater than -1. If x is anything else, x squared is positive and it's going to be bigger. So really I'm just solving this inequality here. So x squared has to be less than 1/3 for this to converge. And then x has to be less than 1 over the square root of 3. So if x is less than 1 over the square root of 3, and then I also want to point out here that when I took the square root, I actually end up with, this part of it back in there. So x could be a negative number, but if x is a big negative number, then r turns into a big value. So the interval of convergence is going to be this right here. So that's the solution to the inequality that we get using the common ratio between -1 and 1 for a geometric series. So if we take a look at another example, I mentioned this when I introduced the idea of using a geometric series. This term here has to be 1 to fit in the form first term over 1 minus the common ratio. So what we're going to do is we're going to multiply the numerator and denominator by 1/2, which is going to get a 1 in that first term in the denominator. So rewriting g of x, we're going to have 7/2 on top over 1 plus 5x over 2. And now in this form, we can say that the first term is 7/2. The common ratio is -5x over 2 to get the minus r part of it. And we can use that now to build our power series. We're looking for four non-zero terms again. So I'll call this m of x for Maclaurin polynomial. And first term is 7/2. And then we're going to multiply by -5x over 2. So it's going to be minus 35x over 4. Then we're going to do plus 175x over 8. And got to multiply that by 5. 675, I believe, over 16. You'll have to check my math on that one. I'm trying to do it without a calculator here. So that's that should be x squared and x cubed also. So again, we take the first term and then we just continually multiply by the common ratio until we get to the point where we've met the conditions in the problem here. Again, I'm going to answer the question, what is the interval of convergence? And the interval of convergence, remember, for a geometric series, the common ratio has to be between -1 and +1. And in this case, the common ratio is negative 5x over 2. So we have negative 1 is less than negative 5x over 2 is less than positive 1. Then we multiply by 2, divide by negative 5, and we have to be careful here. If you divide by negative in an inequality, we flip the inequalities. So we're going to have, I'm going to take this and put it over here for when I flip it. So we have negative 2/5 is less than x is less than 2/5. So our interval of convergence here is going to be for x values between negative 2/5 and 2/5. Our Maclaurin series will converge, and it will converge to the function.